So the questions we have to deal with right now is where those negative numbers came from, right? In the previous video, we saw that when we ran the Fibonacci program, after a while, the numbers became negative, and that makes absolutely no sense because the Fibonacci numbers are increasing positive numbers. Every one is bigger than the previous one, and to get the nth number, we add the two previous ones. So they're getting only bigger and bigger, and clearly they can't be negative, right? So where do the negative numbers come from? So to understand this, we have to understand something about how computers are represented. Look at the general representation for the digits that we use, the base 10 numbers, and then see how we apply that to see how the binary numbers work inside the machine, and see if we can get some insight into this. So let's just take a look at the numbers that we deal with, the base 10 numbers. So let's say I write down the number 126. So I have 126. So why does this represent 126? And in fact, if I were to just take, let's say I took a strip of paper, and I make a window over here, so you can't see the number to the left and you can't see the number to the right. And I ask you what that 2 represents. And the only answer, and you can't see to the left and to the right, the only answer you can possibly give that makes any sense, you have no idea, right? Because let's say if I took the strip away, there'd be a 6 over there, right? And so that wouldn't be a 2, this would be really representing a 20. And if there was a 0 over here, that would be representing a 200, right? So the reason that that's true is because our number system is something called a positional number system, right? It's a positional number system. And what that means is that to find out the value of a number that we write down, you have to take the digits that represent the number and multiply it by the positional values. What does that mean? So in base 10, we know that back in first grade, we learned you had the units position, right? This is the 10 to the 0 position. You have the 10 to the 1 position. You have the 10 squared position, the 10 cubed position. We call this is the ones, the tens, the hundreds, the thousands. So when I write 126, the reason it's 126 because it's one of these, 2 of those, and 6 of them, right? So it's really 1 times 10 squared plus 2 times 10 to the 1 plus 6 times 10 to the 0, right? And so this gives me 100, and this gives me 20, and this gives me 6. When we add them up, I get 126, right? So that's the way this thing works. And there's nothing special, and that's what a positional number system means. The representation takes the digits of the number themselves, and it multiplies it by the positional value, as we saw over here, to get the actual value. So this is true in any base. There's nothing special about base 10, right? We could do this in any base. For example, we can do it in base 16. It's called hexadecimal. Hexadecimal is the number system that's used by programmers for certain applications. It's used in Hogwarts, hexadecimal. And you have base 8, which is also used by programmers. And of course, you can have binary, which is the way numbers are represented in the computer. So let's take a look and see how this applies to binary numbers. So the binary number system is also positional, but instead of the positions being powers of 10, the powers of 2. So we basically get something like this. We get a 2 to the 0 position, a 2 to the 1 position, a 2 squared position, a 2 cubed position, a 2 to the 4th position. So this, of course, this is really what? 2 to the 0 is a 1, and this is a 2, and this is a 4, and this is an 8, and this is a 16, and so on. So the positional values are powers of 2 instead of powers of 4. But now, if I write down a number in binary, right? Binary has which digits? It has a 0 and a 1. Those are the only digits. 1 is the biggest digit, the highest digit. In base 10, the highest digit, of course, is 9. So if I write down the number, let's say 110. So what does that mean? What does that mean? Well, it's the same thing as before. I take the actual digit of the number and I multiply it by its positional value. So I take this 1 and I say it's 1 times its positional value is 2 squared, right? Plus 1 times 2 to the 1 plus 0 times 2 to the 0. Right? What does that give me? 1 times 2 squared gives me a 4, and then 1 times 2 to the 1 gives me a 2, and 0 times 2 to the 0 gives me a 0. So that's how I get a 6. That's why 1, 1, 0 is 6. So what I want to do now is I want you to pause this thing. And what I'd like you to do is, using this idea, I want you to write down all the numbers starting at 0 and going up. Let's imagine we have a computer now that has only 3 positions, right? The machines we use, they have 32 bits per computer word. Some have 64 bits. Imagine we have a very primitive machine that only has 3 positions. So that means you can only have sequences, binary sequences of length 3, right? So what are those sequences going to be? Let's write them in order as binary numbers, right? So you'll have the following sequence starting with 0, 0, 0, and then you'll have 0, 0, 1, then you'll have 0, 1, 0, and then you have, what we have after this, you have 0, 1, 1, and then you'll have 1, 0, 0, and you have 1, 0, 1, and then you have 1, 1, 0, and finally you'll have 1, 1, 1. Now, if I interpret these things as binary numbers using the idea we had before, so in other words, multiplying the digits by the positional values, you'll see that these correspond to the, if I wanted to write down the corresponding decimal numbers, what am I going to get? Well, so this is going to be a 0, right? Because it's multiplying every positional value by 0, and that's going to be a 1, and that's going to be a 2, because it's 1 in the 2's position and nothing else. And this is going to be a 3, because it's a 2 plus a 1, and that's going to be a 4, and this is a 4 and a 1, which gives me a 5, and this is a 4 and a 2 gives me a 6, and this is a 4 and a 2 and a 1, which gives me a 7. So you see, we can represent all the numbers. If I have 3 bits, I can represent all the binary numbers from 0 to 7. How, if I have 3 bits, how would I represent an 8? And the answer is, of course, I can't represent an 8. To represent an 8, I have to go to the next position, and I'm going to have to say I have one of the 8s, and then all the rest would be 0. That would be an 8, right? It's like saying, if I have 2 positions in decimal, how do I represent 100? Well, I can't, because the biggest number is going to be 99, right? It's the same basic idea. So this is very cool. These are binary numbers, and that's how I represent numbers in binary. So there's one hitch here, right? Let's say, for example, I have it in C++. I say have an integer variable I, and I started at 0. That's okay, right? So how would I represent? What would happen if I say I want to make I to be 5? So I simply say I is now going to be 5. That's okay also. But you notice that integers in C++ can be both positive and negative. So how would I say I is equal to -2? How would I say that? Well, I'm in trouble, right? Because I'm using every one of these sequences for positive numbers. And I have nothing left for a -2. And it's not a problem only because I took 3 positions. If I had a 32-bit number and I used all of the numbers to represent positive numbers, I would not be able to represent negative numbers in that range because I'm using up all the sequences, right? So we have a problem here, right? So the question is what to do about it. How do I do this? The answer, if you think about it for a second, is obvious. What's not obvious is how to implement it. What's obvious is that if I'm going to represent negative numbers, well, some of the sequences I'm going to have to allocate to negative numbers, right? Because it's all going to be represented as a binary sequence in there. So if I'm going to use those sequences for both positive and negative, I'm going to say some have to be positive and some have to be negative. So the question is, how do I do the partition? How do I represent the negative numbers? So in order to begin to solve that, we have to ask a more basic question. What's a negative number, right? In general, what's a negative number? So for example, forget about binary for a second. If I have, let's say, the number 3, right? I have the number 3. How would I recognize a -3? How would I recognize a minus? What would a -3 be? So -3 would be such a number that when I added it to a 3, I'm going to end up with a 0, right? It's called an additive inverse, right? It's a thing that makes it to 0, right? It's the same with any negative number. If I have a number n, right, the number n, so minus n is going to be the number that when I add it to n, I'm going to get a 0, right? So we can use that insight over here, right? If I take some sequences and some sequence, if another sequence would make it sort of disappear, make it go to 0, 0, 0, I could say that that second sequence would be the inverse, would be the negative of the first. Okay, let's make that concrete. Let's see how that would work. So let's start simple. Let's start with the number 1, right? So 1 is 1, 1, 1. I mean, sorry, the 1 is 0, 0, 1, right? 0, 0, 1, that's the number 1. So now the question is there anything, any sequence in this whole set of 8 sequences that when I add to a 1, they'll all cancel out and I'm going to get a 0. Now, well, clearly, you know, some of these have to be negative, right? So if I say this is going to be a 0 and I say that's going to be a 1, any of these sequences cancel out that 1. So I suggest you now pause the video for a moment and see if you can find some sequence down here that when you add it to a 1, you'll get a 0. So let's take a look at this guy down here. If I say, if I want to take the 0, if this represents my 1, right? If that's my 1, and I put a 1, 1, 1 over here. So what's going to happen? When I say 1 plus 1, what do I get? 1 plus 1 is 0, right? It's really 2, but 2 is 1, 0 in binary. So it's 0, carry the 1. And 1 plus 0 is 1, plus 1 again is 2, which is 0, carry the 1. And 1 plus 0 is 1, plus 1 again is 0, carry the 1. But we only have 3 bits, so I throw that guy away. And in fact, this really behaves like a minus 1, right? So if some of these are going to be positive and some negative, and I choose to say this guy over here is a 1, then this one over here is going to be a minus 1. What about a 2? Let's see if we can do the same thing here with a 2. So if we decide that a 2 is going to be this over here, right? So if a 2 is going to be a 0, 1, 0, right? 0, 1, 0 is going to be a 2. And any of the ones down the bottom going to erase it, going to make it disappear. So a good suggestion, just because I've done this before, is that this one over here might behave like a minus 2. Might behave like a minus 2. Why would I think that? So first of all, why am I doing it this way? Well, because I noticed that there's something very special over here. I got these numbers have all zeros, these have 1, so maybe there's some complementarity that might be able to be utilized. So let's see if that's really the case. If this 0, 1, 0, if I call that a 2, right, this here, this is a 0, that's a 1, if that's really a 2, let's see what happens when I add 1, 1, 0 to it. So 1, 1, 0. So 0 plus 0 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, plus 1 is 0, and I throw this 1 away because it's only 3 bits. So that, in fact, behaves like a minus 2. If you do the same thing, what about the 3? So I took care of the 0. There's only a 0. The 1, the 2. What about a 3? So what does a 3 look like? What is a 3? So we're saying, what's a 3 over here? A 3 is a 0, 1, 1, right? If that's a 3, 0, 1, 1, and my suggestion is this guy over here behaves like a minus 3. In what sense? In what sense? I suspect that if I add him to a 3, I'll get a 0. Let's see. 1, 0, 1. So 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 0 is 1. 1 and 1 is 0, carry the 1. We throw it away because only 3 bits. So in fact, it does behave like a minus 3. So it's almost as if we're folding the numbers on each other, right? But now, what about this one over here? What does that mean, what about this one over here? So there's really 2 ways to look at it, right? One way is to say, well, look, I can say I have a 0 and a 1 and a 2 and a 3. Maybe he's a 4. Or I can go in the opposite direction. I say I have minus 1, minus 2, minus 3. That's going to be a minus 4, right? Because I know these guys I want to keep to be non-negative to here, right? The 0, the 1. So the question is like this: how do we decide it? So we're going to decide it the same way we did this, right? If it's a 4, let's say, right? If it's going to be a positive 4, so let's just write the number down, right? So let's say we have the number 1, 0, 0. If I say, could it be possibly a 4? Well, if it's a 4, right? If it's a 4, and I added a -1 to it, right? If I added a -1 to the 4, I should get a 3. What did we decide a -1 was? 1, 1, 1, right? From here, we decided that is a -1, right? So let's add a -1. If I add a -1, I'm going to say 1, 1, 1. Let's do the arithmetic. I'm going to get 0 and 1 is a 1, 0 and 1 is a 1, 1 and 1 is a 0, carry the 1 which I toss out, so I get 0, 1, 1. So in fact, I get a 3, right? So that's good, because if that's a 4 and this I call a -1, when I add a 4 and a -1, I get a 3, so that really works. So it seems that that can be a 4, right? So I have this is going to be a 0 and a 1 and a 2 and a 3 and a 4, but not too fast, not too fast. Let's check the other option before we seal the deal here. What about if this 1, 0, 0, right? This 1, 0, 0 were a -4. Just maybe it's a -4, maybe, right? Maybe it's a -4. Well, if it's a -4 and I added a 1 to it, I should get a -3, right? So let's add a 1 to it. A 1 is a 0, 0, 1, 0, 0, 1. So 0 and 1 is 1, 0 and 0 is 0, 1 and 0 is a 1. What number is this? Well, look over here. 1, 0, 1 is a -3. So that means that this guy over here can be a -4 as well. We saw that if I interpreted this thing as a 4, it works. And if I interpret it as a -4, it works. Well, it can't be both, right? When you add it inside the machine, you don't want to give it a nervous breakdown. It's got to decide what to do. So what should we decide? What should we decide this number 1, 0, 0 is going to be? Well, I vote for a -4, right? And I vote that when that number is generated, the machine will treat it as a -4. Why do I do that? Based on what we saw before, right? Because all of these guys, right? All these guys, they have a 0 in the left position, right? And all of these guys, right? They have a 1 in the leftmost position. So it would be consistent that every one of the numbers, or the sequences with a 1 in the leftmost bit, I treat those all as negative, because it actually works, right? You see, those I can interpret it that way, and that will meet all consistent. So that means if I look at a number with a 0 in the leftmost bit, I know that it's non-negative. And if I have a number with a rightmost bit, that's going to be, with the leftmost bit to be a 1, that's going to be a negative number, right? And just notice that there is one more negative number than there is a positive number, and that's because I'm using one of these sequences, namely this one, for a 0, right? And in general, we could do the arithmetic over here. We have how many positions, how many sequences do we have? So we have 2 to the 3 sequences, right? Because I have 2 positions, 2 over here, 2 over here, and 2 over here. So that's what? That's 8, right? But half of them are going to be used for non-negative numbers, right? I want to know what's the biggest non-negative number I can have. So when how do I do that, right? So I divide this thing by 2, so that gives me 2 squared, right? 2 squared, that's the number of sequences over here. But since 1 is for 0, 2 squared minus 1, which is 3, is going to be the biggest non-negative number. And in fact, what about if I have a 32-bit machine? It's the same reasoning, right? The 32-bit machine, the total number of sequences is 2 to the 32. Half of them are going to be non-negative, right? So that's going to give me 2 to the 31. But one of them is going to be 0, So that's the biggest non-negative number that I could have in 32 bits, right? That's half minus 1, right? So that's the biggest non-negative. What's the biggest negative number? So I have, again, I start with 32 bits. I start 32 bits, 2 to the 32. Half of them are going to be negative. So that gives me, so that gives me 2 to the 31 that are negative. So minus 2 to the 31 is the biggest negative number. That's this. And what I want to do before we finish this thing here is just take a look at some arithmetic, specifically, how do we do subtraction, right? We looked at adding. What about subtraction? How does subtraction work? So let's take a look at that. And we'll look at it in the context of decimal numbers, and then we'll see that the same thing sort of works with a binary. I don't know if you ever try to teach arithmetic to kids, but they get hung up sometimes on subtraction. So I'm going to show you a magic trick, which is really cool. Let's say that I have, let's say, the number 87. Right? I have 87. Let's do this in blue. Right. So I have 87, and I want to subtract, let's say, 23. So 87 minus 23, 3 from 7 is 4, right? And 2 from 8 is 6, so that gives me 64. Is that right? That's right. So here's a way to do this. What we're going to do is we're going to change this subtraction into an addition. And what we're going to do is we're going to do it by transforming this bottom number. So what I do is I take the bottom number like this. I write down a 23 like that, and I write a 99 on top of it. And what I ask is, for every number here for this 23, I go to the 3 and I say, what number do I have to add to the 3 to make a 9? Well, I have to add a 6 to the 3 to make a 9, right? What do I have to add to the 2 to make a 9? I have to add a 7 to the 2 to make a 9. So now what I do is I take the original number, which is 87, and instead of subtracting the 23, I'm going to add the 76. So I'm going to say, add the 76. So how much is 7 plus 6? Well, that's 13. So it's 3 carry the 1. How much is 8 and 1? That's 9. 9 and 7 is 16. I write down the 6. I have a 1, but I'm only dealing with 2 digits over here. But it's a shame to throw the 1 away. So I put the 1 on the bottom, and I get a 64. Unbelievable, right? So what I did was I took a subtraction and I made it into an addition, and I just was ashamed to throw ones that are useful. So instead of throwing the pennies away, I just added at the bottom, and it really works. So this is a trick, right? But it's an interesting trick, and in fact, this is the trick that's used to make computers subtract numbers. Let's see, does it work for something else, right? Let's say I want to subtract, I have an 84, and I want to subtract a 56, right? I want to subtract a 56. So try working that out, and then we'll do it together. Make sure you understand how this thing works. So we want this 84 minus 56, so let's transform the bottom part. And we do the same as we did before. We write a 99 over here, and we put the 56 down here. And we say, how much do I have to add to the 6 to make a 9? And that's going to be a 3. And how much do I have to add to the 5 to make a 9? That's going to be a 4. So I've taken this negative, the subtraction, and I want to transform it into an addition. So I have the same 84 on the top, but instead of subtracting the 56, I'm going to add a 43. So plus a 43. So 4 and 3, that's going to be a 7. 8 and 4 is 12. I have that pesky little 1, so I'm going to bring it down over there, add the 1, and I'm going to get a 28. So it matches, right? Even when I have to borrow, in this case, I borrowed because the 4 is bigger than the 6. So this thing really, really works. Now, it's not such a magic trick, right? The way that it works is this transformation, this part over here, this transformation, when I take the 56 and put on the bottom and add how much do I have to add to the 5 and the 6 to make a 99, I'm going digit by digit. The 43 is called the 9's complement. 9's complement. And when I add the 1 in the bottom, right, I could just have as well added it right over here. That's called the 10's complement. And this trick is called doing subtraction by doing the 10's complement arithmetic. What I do is I take the 10's complement of the bottom number and I add it in and I throw away the leftmost digit, and it works. The question of why it works is interesting. You can just take a look at what's going on by yourself. If there's a question, you can email me and maybe I will put it into a subsequent video, but I want to get to the next topic and take a look, how does this thing work for binary numbers as well? But there's a very neat trick for doing subtraction, which is explain how it works again. If I want to subtract B from A, so I take A, and instead of subtracting B, I get the 10's complement of B, and let's call it B prime, and what I do is I say A plus the complement B prime, and that's going to give me, and I throw away the leftmost digit, and that gives me A minus B. It's a very cool idea, and in fact, that is really the way that the computer subtracts numbers, except that we do it with binary numbers, right? And so we're going to get the complements of binary numbers. To see how that works, just let's again remind ourselves, let's go back to the base 10. So in base 10, we saw there was a 9's complement, and then we added 1 to make it a 10's complement, and we added the 10's complement to do the subtraction. So let's go, for example, if I write the number 346, right? What's the complement of 346, right? If I want to make minus 346, basically, right? So what I do is I say, let me go, and to see each digit, why do I have to make it to a 9, right? So 6 to make it a 9 is a 3, 4 to make it a 9 is a 5, and 3 to make it a 9 is a 6. Now, why do I say to make it a 9? Because what I do is I say I want to get to the highest value in that particular base. So in base 10, since the digits go from 0 to 9, the highest value is 9, right? So I say, what's the complement to get to 9? That's the 9's complement, right? We saw that's called the 9's complement. And then to make the 10's complement, I simply added a 1. So 654 is the 10's complement. So the same idea is when I'm dealing with binary numbers, except with binary numbers, since the digits are 0 and 1, the highest value I can get is a 1. So let's take a look. Let's imagine what's going to be, how do I represent a minus 2, right? So we saw to represent a minus 2, if I take a 2, a minus 2 is going to be the number that when I add it to 2 gives me a 0, right? So basically, and it behaves like a minus 2 because if I add it, say, to a 3, I'm going to get a 1, right? If I straight 3 plus a minus 2, I'm going to get a 0. So, and we actually worked that out, and we saw that these minus 2 turns out to be this, right? Because it worked, right? We saw when we added it to a 2, it behaved like a 0. We got a 0 out of it, and we added it to a 3, we got a 1 out of it. So it actually worked. So how do I go about doing this? What does the computer do when it generates it? So let's take the 2. So basically, we take a 2, and let's see what happens. We get its 2's complement. So we go 0, 1, 0. That's a 2, right? And then we say, let me write down 1, 1, 1. That's the equivalent of before we wrote out 9, 9, 9. And I'm going to say, what do I have to add to the 2 to make it to the 1 to this number down here, right? These numbers to make a 1, the highest value. So to a 0, I just have to add a 1. To a 1, I don't have to add anything, right? So that's going to be a 0. And to the 0, I have to add a 1, right? So the complement, this is the 1's complement, right? Because I simply say, I want to complement this value here to bring it to a 1. So to a 0, I have to add a 1. To a 1, I don't add anything. And to a 0, I have to add a 1. So that's the 1's complement, but I want the 2's complement, right? The 2's complement. So I have to add a 1 to this. So 1 and 1 gives me 0, carry the 1. 1 and 0 gives me, because it's the carry, 1 and 0 gives me a 1, and then the 1 over here, right? And I count that down. So my claim is 1, 1, 0 is what is going to represent -2. And lo and behold, right, this is my representation for -2. If I look at the one we got before, this is in fact -2. So that's how 2's complement works. It's basically the same idea that we saw before. So you simply, because the 1's complement, you sort of flip the bits, and then you add 1. And this is done in the computer. That's the way you subtract, right? If I want to subtract some number n, if n is a positive number, I simply take the binary representation, I flip the bits. That's what it means to complement it, right? Let's look over here. Let's look over here. When I complemented the 0, I basically flipped the bit, right? When I said, what do I need to add to make the 0 to make a 1? I simply said, well, flip the bit, right? So 0 became a 1, 1 became a 0, 0 became a 1, right? So that's really what's going on. It's called complementing, and the hardware is built in. It automatically does it, right? So there's a complementer inside the hardware, and then there's an adder also as part of the hardware. So to do subtraction, you don't need any new circuitry. You simply flip the bits to get the representation. To do the minus, you flip the bits, you add a 1, and that becomes your negative number. So that is the way it works. And it's really very cool.